Hello everyone! When we learned about the concept of geometric sequence earlier, we learned that geometric sequence is closely related to real life. For example, problems such as cell division and bank loans can be solved using knowledge of geometric sequences. Today, we will continue to explore the first n terms of geometric sequence and related application issues. Let's first review the first n terms and formulas of the geometric sequence. The formula for the sum of the first n terms of a geometric sequence requires a classification discussion based on the common ratio q. When q equals 1, Sn equals n times a1. When q does not equal 1, there are two forms. Sn equals the first term a1 multiplied by 1 minus the nth power of the common ratio q divided by 1 minus the common ratio q. Alternatively, Sn equals the first term a1 minus the nth term n multiplied by the common ratio q divided by 1 minus the common ratio q. The basic quantities involved in the formula vary. You need to first analyze which quantities are given in the problem, such as the initial term a1, the common ratio q, the number of terms n, and the nth term n, and select the most suitable formula to solve. Let's move on to question 2. As shown in the figure, in a square ABCD with side length 5, take the midpoints EF and GH of each side of square ABCD to form a second square EFGH. We then take the midpoints of each side of square EFGH to form a third square, IGKL. Continue this method. For the first question, find the sum of the areas of 10 consecutive squares starting from square ABCD. First, let's consider how to find the area of each square. We know that the area of a square should be equal to the product of its side length. Therefore, we need to know the side length of each square first. What is the relationship between the side lengths of each square? Let's try to list them out. Firstly, the side length of the first square is 5 centimeters. We can derive the side length of the second square as 5 times the square root of 2 centimeters using the Pythagorean theorem. Similarly, applying the Pythagorean theorem again, we can obtain the side length of the third square as 5 times the square root of 2 centimeters. By analogy, let the side length of the kth square be a. Then the side length of the k plus first square should be a multiplied by the square root of 2 divided by 2. We have drawn a conclusion. Let the side lengths of these 10 squares constitute a sequence n. Then n is a geometric sequence with 5 as the first term and the square root of 2 over 2 as the common ratio. Let's see. After understanding the relationship between the side lengths, let's explore the relationship between the areas of each square. Firstly, the area of the first square should be equal to the product of its side length 5 and itself, which equals 25 square centimeters. The area of the second square is equal to the product of its side length 5 second multiplied by the square root of 2, which equals 25 second square centimeters. Similarly, we can calculate the area of the third square as 25 fourth square centimeters. Okay, let's assume the area of the kth square is a times a, which equals a squared. Then the area of the square following the kth should be calculated by multiplying the side length of the square following the kth, which is a times the square root of 2 divided by 2 by itself, resulting in an area of a squared divided by 2. Therefore, we draw the conclusion that if the areas of these 10 squares constitute a sequence Bn, then Bn is a geometric sequence with 25 as the first term and 1/2 as the common ratio. So, how can we find the sum of the areas of 10 consecutive squares? That's right, finding the sum of the areas of these 10 squares is equivalent to finding the sum of the first 10 terms of the geometric sequence Bn. So we know that when the common ratio q is not equal to 1, there are two formulas for the sum of a geometric sequence ... In the given problem, we know that the first term b1 is equal to 25. The common ratio q is equal to 1/2. Therefore, we choose the first formula to solve. Let's try to solve the problem. Assuming the area of the square ABCD is B1, and the areas of the subsequent squares are denoted as B2, B3, and so on up to Bn, then B1 equals 25. Since the vertices of the kth plus 1 square are located at the midpoints of each side of the kth square, the area of the kth plus 1 square should be equal to half the area of the kth square. Let the area of 10 squares constitute the sequence Bn. Then the sequence Bn is a geometric sequence with 25 as the first term and 1/2 as the common ratio. Let Sn denote the sum of the first n terms of the sequence Bn. Then we can derive that Sn equals the first term 25 multiplied by 1 minus the ratio 1/2 to the 10th power divided by 1 minus the ratio 1/2. By simplifying this expression, we ultimately obtain the result as 25,575 divided by 512. Thus, we have obtained the sum of the areas of 10 consecutive squares starting from the square ABCD. Let's move on to question 2. If this drawing process can continue indefinitely, what will the sum of the areas of all these squares infinitely approach? We have obtained the areas of the squares, forming a geometric sequence with 25 as the first term and 1/2 as the common ratio. Then, how should we represent the sum of the areas of these squares when n tends to infinity? That's right, we can represent it using the formula for the sum of the first n terms of a geometric sequence. Observe this formula. Let's consider what factors affect the change in sen. Indeed, the variation of Sn should have a direct relationship with n. Let's analyze it. When n becomes infinitely large, we know that the graph of the exponential function y, which equals 1/2 raised to the power of x, corresponds to the case where the independent variable takes positive integer values. Therefore, as n becomes infinitely large, 1/2 raised to the power of n will approach 0 infinitely. At this point, 1 minus 1/2 raised to the power of n will approach 1 infinitely, so Sn equals 25 multiplied by 1 minus 1/2 to the power of n divided by 1 minus 1/2. It can be rearranged as 50 multiplied by 1 minus 1/2 to the power of n. When this expression approaches 1 infinitely, the whole will approach 50 infinitely. Therefore, we know that when n increases infinitely, Sn will approach the sum of the areas of squares infinitely. So the sum of the areas of all these squares will approach 50 infinitely. Here we use the idea of limits. The limit value refers to a value that represents a stable trend and direction of change during a certain process of variation. The concept of limits is an important idea in static mathematics. We should understand and apply the concept of limits to analyze and solve problems. Let's move on to question 3. Last year, a certain place produced 200,000 tons of household waste, of which 140,000 tons were disposed of through landfilling. 60,000 tons were disposed of in an environmentally friendly manner. It is estimated that the total amount of household waste will increase by 5% annually. At the same time, the amount of waste disposed of through environmentally friendly methods will increase by 15,000 tons each year. To determine the budget for disposing of household waste, please predict the total amount of waste disposed of through landfilling over the next 5 years, starting from this year, accurate to 1,000 tons. Let's first consider what relationship exists between the total amount of household waste generated each year. That's right, the total amount of household waste increases by 5% every year. Let's try to list it out. Last year, the total amount of household waste was 200,000 tons. This year marks our first year. Taking 20 as the base number and multiplying it by the annual growth rate of 5%, we get an increase of 20 times 5% for the first year. Adding the base number 20, we get the total amount of household waste for the first year as 20 times 1 plus 5%. Similarly, let's look at the second year. In the second year, we take the base number of 20 multiplied by 1 plus 5% and multiply it by the growth rate of 5% to get the growth amount. Then, we add the base number of 20 multiplied by 1 plus 5% to get the total amount of household waste in the second year, which is 20 multiplied by 1 plus 5% squared in tons. By analogy, we can derive the third point, the total amount of household waste in the fourth year. Observing the formula, we can draw a conclusion that from this year onwards, the total amount of household waste constitutes a geometric sequence with 20 multiplied by 1 plus 5% as the first term and 1 plus 5% as the common ratio. Let's consider this further. What does the amount of waste disposed of in an environmentally friendly manner each year matter? The amount of waste we dispose of through environmentally friendly means increases by 15,000 tons every year. Based on this, let's list out the details. Last year, the amount of garbage disposed of in an environmentally friendly way was 60,000 tons. Starting from this year, which is the first year, we use 6 as the base number and add the annual growth rate of 1.5. Therefore, the amount of garbage disposed of in an environmentally friendly way in the first year is 6 plus 1.5, which equals 75,000 tons. Then in the second year, we take 6 plus 1.5 as the base number and add the growth amount of that year, which is 1.5, to get the amount of garbage disposed of in an environmentally friendly way in the second year, which is 6 plus 1.5 times 20,000 tons. Keep adding, and we can obtain the values for the third and fourth years. Thus, we have drawn the conclusion that, starting from this year, the amount of garbage disposed of in an environmentally friendly manner constitutes an arithmetic sequence with 6 plus 1.5 as the first term and 1.5 as the common difference. So far, we have determined that the total amount of household waste each year from this year onwards constitutes a geometric sequence. We can write its general formula as a n equals 20 multiplied by 1 plus 5% raised to the power of n. We have also found that the amount of waste disposed of in an environmentally friendly manner each year from this year onwards forms an arithmetic sequence. Similarly, we can also write its general formula as Bn equals to 6 plus 1, 5n. Let's consider how to represent the total amount of waste disposed of through landfill each year. Indeed, we simply need to subtract the amount of waste disposed of in an environmentally friendly manner Bn from the total amount of domestic waste An for that year. Alright, let's calculate together. Let n represent the sequence of the total amount of household waste generated each year from this year onwards. Let Bn represent the sequence of the amount of waste disposed of in an environmentally friendly manner each year. If the total amount of waste disposed of through landfill within n years is n, then n equals 20 multiplied by 1 plus 5% raised to the power of n, and Bn equals 6 plus 1.5n. At this point, Sn equals a 1 minus b1 plus a 2 minus b2, and so on, until a n minus bn. Let's think about how to sum this formula. Observing the structure of the formula, it is not difficult for you to find that a 1, a 2, a n in the formula belong to a geometric sequence, while b1, b2, bn belong to an arithmetic sequence. Therefore, we may divide this formula into two groups. The first group involves the summation of a geometric sequence, while the second group involves the summation of an arithmetic sequence. We can obtain the value of Sn by subtracting the sum of the second sequence from the sum of the first sequence. Let's try to calculate it. Firstly, based on the given conditions in the problem, we can derive that the sum of the first n terms of the sequence n is equal to the first term 20 multiplied by 1.05 raised to the power of 1 minus the common ratio 1.05 raised to the power of n, divided by 1 minus the common ratio 1.05. Then the sequence Bn is an arithmetic sequence, and its sum of the first n terms should be n times the first term 6 plus 1.5 divided by 2, plus the nth term 6 plus 1, 5n, for this equation. We can simplify it to obtain 420 multiplied by 1.05 raised to the power of n, minus 3/4 times n squared, minus 27/4 times n, minus 420. When n equals 5, we can calculate that S5 is approximately equal to 63.5 using a calculator. Therefore, within 5 years from this year, the amount of garbage disposed of through landfilling will be approximately 635,000 tons. Through calculations, we have come to understand that the amount of garbage generated annually from daily life and production is a staggering figure. Disposing of this garbage is a task we have to face, which inevitably serves as a warning to us. Let's summarize the approach to this problem. This question involves a comprehensive application of the formulas for the sum of the first n terms of an arithmetic sequence and a geometric sequence. Based on the actual problem scenario, we can construct two sequences. The total amount of household waste increases by 5% annually, forming a geometric sequence An. The amount of waste treated through environmentally friendly methods increases by 1.5 each year, forming an arithmetic sequence Bn. The quantity directly related to solving the problem, which is the amount of waste disposed of through landfill each year, can be represented by the difference between these two sequences, An minus Bn. Thus, finding the amount of waste disposed of through landfilling within n years is equivalent to finding the sum of the first n terms of the sequence An minus Bn. To solve for the sum of this unfamiliar sequence, we need to convert it into a problem involving the sum of an arithmetic sequence or geometric sequence that we already understand. By grouping and summing, we can obtain the solution to the problem. Summary of this class. 1. Master the mathematical model for solving problems such as growth rates using geometric sequence knowledge, paying particular attention to the selection of common ratio and number of terms. 2. Based on practical problems, we must first distinguish between geometric sequence and arithmetic sequence, and then establish different mathematical models. 3. I hope everyone can discover the different characteristics of arithmetic sequence and geometric sequence through practical problems. That concludes our lesson for today. I wish everyone a pleasant learning experience. Goodbye, everyone.